One down.
Okay.
Hello.
So to start off for today, first thing I wanted to do, on Friday, we introduced these concepts dealing with rotational motion. And we talked about the idea that it is motion, so we're still dealing with these three things, displacement, velocity, acceleration. But how we define them has to change, just because it's a different kind of motion. But it's still motion, so we still include those things. Okay? And I think yesterday no one mentioned this, but if not, here, up on the board, right, there are three definitions as far as what we're doing, or how we define those different things. You know it's all of you. Up on the board yesterday, we put up these three definitions of how we define displacement, how we define velocity, how we define acceleration. But the one thing I wanted to do today was, on Friday we introduced this, but our kinematic equations, back when we were talking about linear motion, were relationships between displacement, velocity, acceleration, and time. If we accelerate for this long, what happens to our velocity? If we accelerate for this long and we were going this fast to begin with, how far do we end up going? All of those different descriptions of motion are related through velocity, acceleration, time, displacement. Okay? But because this is still motion, granted it's a different kind of motion, but it's still motion, these relationships still hold true. Just we define them a little differently. We talked about that these were the four kinematic equations, and I posted them up here, but they're a little bit hard to see, okay? But if we know the conversions between the rotational quantities and the linear quantities, you can just look wherever you used to look to find your kinematic equations and know what they are. That was, that's like if we convert from the rotational quantity to like the tangential, okay? But here we're just talking about describing the rotation of that object. So like something speeding up or slowing down as it's spinning. Does that make sense? Okay. So if we look here up on the board, as long as you know the conversions, you have all those equations up on the board. For instance, anytime we see an omega, right, the curvy W, that represents our rotational velocity. So anytime that there's a v in one of these kinematic equations, there's going to be an omega in the rotational kinematic equations. Okay? Alpha represented the acceleration. So anytime that there's an a in one of our linear kinematic equations, there's going to be an alpha. Right? Theta represented the displacement. So anytime there's a distance or how far did we rotate, et cetera, that's going to be theta. And then time is just time. That doesn't change, depending on where we're going, rotation versus linear. Okay. Good with that? Let's run through one of these just so we have a little bit of an idea. I think you'll find that after we do one example problem, I think we probably got the gist of it. So let's go here on the sheet. Let's take a look at number 1. So, as far as number 1 is concerned, on popular evening game shows, contestants spin a large wheel to earn fabulous cash and prizes. No names, please. One contestant spins the wheel giving an initial angular speed of 3.4 radians per second. The wheel rotates through 1 1/4 turns before coming to rest. So, part A, what is angular acceleration of the wheel? Part B, how long does it take the wheel to rest? Okay? Doing problems here, exactly the same as doing problems before. So, first step. What is our first step in doing this problem? Find out what we're looking for, right? So for part A, right, what are we looking for? Not omega, alpha, that's the fish. Right? So for part A, angular acceleration represented by the fish. Okay? Then, part B, how long does it take for the wheel to come to rest? That's just asking us what? That's time. Okay, so delta T is going to be our unknown for part B. Okay? Good there? All right. What are we looking for? What's the next step? What do we know? So, what's something that we know? Angular speed. Which angular speed? An initial. So that's going to be omega. Okay? So that's omega initial is 3.40 radians per second. Okay. What else did they give us to work with? Okay. It tells you like how much it rotates, right? Bender, what is that? Let's give you a variable first. What variable is that? That's going to be our angular what? How far is some displacement? Okay. So that's going to be our theta value. Okay. And like we said, it's 1.25 rotations, right? But do we want theta in terms of rotations? We want it in terms of what? Radians, right? So you don't have to do this necessarily, okay? But as far as conversion goes, right, we can convert rotations into radians, right? What do we know about rotations versus radians? One rotation is 2 pi radians. So we can convert that theta from rotations into radians, okay? Don't leave it in terms of pi. Actually get it out, actually give it a number. Okay?
Why 1.25?
It says that the wheel rotates through 1 1/4 turns, right? Okay. So that's a how far, right? But we don't want it in terms of turns. We want it in terms of radians. Okay.
I'm saying how did you know like 1.25 could equal 2 pi radians?
This is the important part here.
Yeah, no, I know that. But
Okay.
it's just the same for the 2 pi rotation.
Yeah, but here it's not always one rotation. Right? In this problem, it wasn't one rotation. It was 1 1/4 rotation, 1 1/4 rotation. This will stay the same for any problem.
But that 1.25.
This might change.
Yeah.
Yeah.
That's what I'm saying.
I think it's 7.85, right? When you bulk it up. All right. What other? In doing the fact that we're doing a kinematic equation, right? How many pieces of information do we need? We need 3, right? We have 2 right now. What's the third piece? What happens on Wheel of Fortune? It stops spinning, right? It slows down, yes, but eventually it does what? Stops, yeah. So that means that omega final is going to be equal to what? 0, so radians per second. Now, doing these 2 problems, doing part A and part B, is just like doing linear kinematic equations, right? Each of our rotational kinematic equations has 4 variables in it. You need to pick the one that has the 3 variables that you know and 1 variable that you're solving for. All right? So why don't we go ahead and do that? Let's take a couple of minutes and just run that through, get some answers, and then we'll move on to the next thing. equations. They are available for you up on the board.
Wait, alpha F is, that's not alpha. Omega F is 0 because there's a stop.
But that eventually that thing's going to stop spinning, so it's going to go 0 radians per second. It's not rotating at all anymore. Alright, we good here with these two? Any questions? I think you'll find that if you go along and continue with the other problems that are on this page, you'll find that the pattern holds true, right? What are we looking for? What do we know? Pick the right kinematic equation that goes along with it. Okay? If you get adventurous and you feel like doing a couple more of those, on Monday's date, the 9th yesterday, there are answers posted for those, so you can find them there. Good? All right, let's shift gears for a second